Okay, let's get started here. So, project number 2 is due on Wednesday at noon. Test number 1 is 1 week from today. On Thursday here, we will spend a large portion of the class reviewing for the exam, so please bring questions if you have them. We can spend some time answering the questions then. Okay. Also, I want to make a comment too about there was a message this weekend that was mistakenly posted to the listserv, as I think some of you saw. Please be careful and don't do that. It's quite easy, and this usually happens about once per semester in my classes. It's quite easy to make that mistake. So, and here's why. So here's hopefully you can read this. So I used, for example, Outlook 2010, and here was a message that I posted, or this is an email that I received from the listserv from a message that I posted there. And you can easily, if you see where my mouse is, you can easily think that this was actually sent by me rather than the listserv. So what I often have students do is that they'll just click on reply thinking that the message was for me, and so it will be sent directly to me, any additional messages, when in fact it's actually sent to the listserv. So please be careful about when you hit a reply on one of these kinds of messages that you know exactly where it's going. I've had some quite embarrassing emails sent to the listserv by students who had intended to actually email me. The most embarrassing email or message that was posted to the listserv happened a few years ago, and often I will have students email me to let me know that they're not going to make it to class, let's say today or some other time, because they are sick. And so what sometimes happens is that emails that are meant for me about that they are sick are posted to the listserv. And generally speaking, most students in class don't care if you are sick and not coming to class. But the most embarrassing thing that has ever happened was I had 2 students who were friends in my class a few years ago, and one of the students was sick, and I guess was unable to email me to let me know, so the friend decided to email me to let me know that that student was sick and not going to be able to attend class. And both of these students were non-native English speakers, okay? And the student who had thought he was just emailing me, but instead posted it to the listserv, wanted to tell me that so-and-so wasn't going to be able to attend class because he's having some severe loose movements. Now, I admit that when I first read that message, I wasn't sure exactly what they meant by loose movements. I'll let you think about it for a second if it's not totally clear. And so now this got distributed across the entire class. Please don't be that kind of person to let everyone know that you are having loose movements. But anyway, just be careful about that. Are there any questions before we get started here? Okay, so we are now starting chapter 4. This stuff is not on the exam. Of course, that doesn't mean you should just ignore what I'm saying for the next hour or so, but it's not on the exam. It will be on test number 2, of course. And so chapter 4, we're going to go through the chapter quick, so we're not going to do everything that's in there. Chapter 4 contains a number of, let's say, disjoint topics. And I'm going to pick and choose some topics. Some topics are more important than others, and I'm going to choose the more important ones. And this first topic involves the joint estimation of beta 0 and beta 1. And what the book is talking about in this particular case is that, often we would like to be able to look at confidence intervals for these corresponding parameters, or in fact, you could do hypothesis tests for these corresponding parameters. You want to do them for both. Now, if we're doing a confidence interval, you might find a 95% confidence interval for beta 0 and find a 95% confidence interval for beta 1. But what's the overall, let's say, confidence level that you have that both intervals actually contain the corresponding parameters? That overall confidence level is not 95%. Instead, it's going to be something typically lower than 95%. The problem is it's kind of difficult to figure out exactly what that level is. If you could actually say that these inferences were independent of one another, one could use a binomial distribution and find that that confidence level that both inferences are working as intended would be 0.9. But the thing is that these inferences are not independent of one another, so you can't exactly do that. So in order to at least try to control this confidence level to be maybe at least some particular level that you specify, what we need to do is define what's called a family confidence level. So first of all, a family, at least that term that's often used in statistics, is often with respect to you're making multiple inferences, and you're kind of grouping these all together into a family. And what we like to be able to do is control the overall family confidence level. Or if I'm doing hypothesis tests, control the overall type 1 error rate. Now, so far, what we've been primarily focusing on is just the individual confidence level. So I have a 95% confidence interval here. I have a 95% confidence interval here. What the family confidence level then is the confidence level that all the intervals contain their corresponding parameters. That's what we're going to be interested in trying to control at a specified level. There's a variety of ways to do this. We're going to focus on just one way in this class called a Bonferroni, I guess you could say, adjustment or correction so that you do control the family-wise confidence level. I anticipate that probably all of you have seen the Bonferroni procedure before. At least when I teach Stat 801, I talk about the Bonferroni procedure, that is the prereq. If not, that's okay. It's a fairly easy procedure to understand. And also, many of you probably not seen it in a regression context before. So let's say, to help motivate where this Bonferroni procedure comes from, let's say I have some kind of event. Let's call it A1, and it's the event that beta 0 is not in the confidence interval. Let A2 be the event that beta 1 is not in its corresponding interval. Then we could say then the probability that at least one confidence interval does not contain that corresponding beta is simply probability of A1 union A2, where I use that little u there to mean union. Maybe some other, in some other classes you've had, maybe instead of the little u symbol, maybe just simply or was given. And what this just basically means, A1 union A2 means that either A1 is true and A2 is not true. A2 is true, but A1 is not true. Or all of them are true. So at least one. Well, the probability then that both confidence intervals actually do contain the parameters can be found from taking the complement. And please note that there is a small error there, so please make that change in the notes. So complement is, the opposite of an event. When we're working with probabilities, if I have, let's say, an event B, the probability of B is equal to 1 minus the probability of B complement. So either it's B or B complement, 1 to 2. And through an application of De Morgan's laws, you remember those from your first stat course, we can show then that the complement here, when we write this out in terms of a probability, is 1 minus A1 complement intersect A2 complement. So again, let me emphasize the notation here because different introductory stat courses use different notation. So the little upside down U denotes intersect. Some classes might actually write that out as the word and instead. The little line on top of A1 is a way to denote the complement, the opposite of A1. You know, other classes often will use this notation, maybe with a little C instead as a superscript, or they might actually put a little prime mark there or a little tick mark there to mean complement, same thing. I'm just using bars because that's what our book does. So what that means then for us too is that the probability of A1 complement intersect A2 complement is equal to 1 minus the probability of A1 union A2. So again, remember what this part here means. Both confidence intervals contain beta 0 and beta 1. Or I should say one interval contains beta 0, the other interval contains beta 1. Please note again the change on page 3. So also what we can do is use the old addition theorem of probability. Maybe it was called something slightly different in your first stat course. But that formula should look familiar. Probability A1 union A2 is equal to probability A1 plus probability A2 minus probability A1 intersecting 2. So what I could do then is rewrite this as 1 minus, put a 1 minus here as well. And well, what's this 1 minus part here? That right there. And so that's what's on top of page 4.3. And then lastly here, I can take then the probability that all intervals are working, containing their corresponding parameters, to be greater than or equal to 1 minus the probability A1 minus the probability of A2. Well, why can I do that? Yeah, so this is always positive, so if I take that out, then now I have a greater than there. Okay? So what this says then is that I know the probability that these intervals work has to be greater than 1 minus the probability that one interval does not work minus the probability the other interval does not work. So in our application then, this is how this is going to help us. If I want to find, let's say I found 95% confidence intervals for beta 0 and also one for beta 1. So that's the individual, let's say, confidence level. Then what that means is the probability that both intervals are working is at least 1 minus 0.05 minus 0.05. In other words, 0.9. So my family confidence level is at least 90% if I use 95% confidence intervals. So in other words, I get a lower bound. It could be a lot higher, but I know it's at least 90%. What this also provides is a way to now go the opposite direction. Let's say that I want to control my overall confidence level, my family confidence level to be 90%. Then, you're working backwards, you can say, well, then that means I need to use 95% confidence intervals for each parameter. So that in general then, if I want to have, let's say, if I want to have a family confidence level of, let's say, 100 times 1 minus alpha percent, what that says is then I should take my other two intervals, I should take the individual intervals to be 100 times 1 minus alpha divided by 2 percent intervals. Is everyone clear on that? Any questions?
Is there a reason why both confidence intervals have to be at the same level?
They don't have to be at the same level, but obviously it's convenient. So what this is assuming then is that each of the individual levels, or each of the individual intervals are at exactly the same level. I think it would be hard to justify to someone typically that, oh, I want a 99% interval here, but I want a 90% interval here. I mean, there are some statistical methods out there that often what's called sequential testing, where you might do a test here, and then depending upon the result, do another test here, and then depending on the result, do another test here. And someone's watching golf right now. Okay. Anyway, and so what they will do is they will actually proportion out. You can think of it like spending your alpha levels, and put some here, put some here, and put some here. That's the only application I've ever seen where they would have different confidence levels. Well, let's take this further. Let's say instead of just instead of having a model such as this, what we're going to be starting to talk about shortly in Chapter 6 is that let's say that you have now a model that has two predictor variables, one called beta 1, one called beta 2, and I just add another beta to the model. And let's say that I want to find confidence intervals for each of these betas. So now I have 3. But I still want to control my family confidence level to be 100 times 1 minus alpha, 100 times 1 minus alpha percent. What should I take for the individual intervals as their confidence levels? I think I heard the answer. Replace that with a 3. So let's say now in general, let's say that I want to go out to, g different variables. I'm sorry, let's do g minus 1. Suppose I want g minus 1 variables, then, I don't know why my toolbars always disappear now. Then if I want g different intervals, I put a g there instead. What's going to happen as g gets big? Well, the individual confidence intervals will have a higher and higher and higher confidence level. What happens to intervals as their corresponding confidence levels get higher? Excuse me?
Wider.
They get wider. So if G is large, you're going to have perhaps some very, very wide individual confidence intervals. So this is one problem then with the Bonferroni procedure. And that is that you can get very wide intervals if you have a large G. So please take note of that. Now there are other procedures out there though that you can use. In particular, the book talks about something called the Chaffee procedure that would not necessarily have that problem for a large G. You'll still have wider intervals, but maybe not as wide as a Bonferroni procedure would. I'm not going to talk about the Chaffee procedure in our class, but if you're interested, the book does talk about it some. Are there any questions? Okay. So back to the case where let's say G is 2, so I want G intervals itself. Look what happens to our formulas for a confidence interval for beta 0 and beta 1. Where before where I would have a 2 here, now I have a 4. So in essence what I'm doing is taking 2 times G. Is everyone okay with that? Why that's a 4 instead of a 2? Okay, silence means yes. Let's take a look at a quick example. This is with the high school and college GPA data set again. So I read in my data. I estimate my model like I normally do. This time, just to make the output look a little bit shorter, because we don't need all of it, I put the summary of mod.fit in an object called sum.fit, and I simply extract a component called coefficients. And basically what I have here is a portion of the output that we normally see. That contains the beta hats, the standard errors, the test statistic values, and corresponding p-values. I set alpha to be 0.05. What this is going to allow me to do is have a family confidence level of 95%. G is going to be 2 because I'm going to have 2 intervals. And then I find my quantile for my t distribution like we would normally do, but notice where the G falls in. So then it's just a matter of, I'm not going to go through all the details, it's just a matter of putting in the correct numbers in the same places that we saw back in Chapter 2. The only difference is that we have a new t distribution value. That's all. So then interpretation then is that we are at least 95% confident that beta 0 is between 0.22 and 1.19, and beta 1 is between 0.52 and 0.8787. So that's the interpretation. Again, notice the elites. How could we do these calculations completely in R? It's not too difficult. I won't go through all the details. I'll just point out one small thing. Notice what I can do here. Sum.fit $coefficients. I have a row number, and then I have a column number corresponding to this part right here. So what I'm doing is I'm pulling out the standard errors from sum.fit $coefficients and using them in the appropriate locations in my code. Lastly, the easiest way to do this, though, is to use a function in R called conf_int, confidence interval. You just can simply say object equal mod.fit, and this conf_int function is what's called in R a generic function, and since it sees that mod.fit has an LM class, it's going to think, okay, you want confidence intervals for the betas. And well, what level do you want to use for each individual interval? 1 minus alpha divided by G, where G is 2. Yeah?
Does that confidence interval function just work for the coefficients then?
It only works with respect to a regression model here. It only works with the coefficients.
Okay.
But if you take other classes, you will find that this conf_int function works in a variety of other places too for other kinds of models. Other questions? Okay, so it's not not too difficult, but it is a nice little thing here to make sure that you have a higher level of confidence, or that you're, let's say, you know at least what your level of confidence is. Now this next stuff just basically follows from what we just talked about. Set of confidence intervals for the beta. Suppose you want now confidence intervals for the expected value of y, and you want to control the overall family-wise confidence level. Well, how would you do that? As you would expect, if you use a Bonferroni procedure, and now put a G in the formula that we had previously. That's it. So where G represents the number of intervals you want. So, for example, with the college and high school GPA, suppose I want confidence intervals for the expected value of y at 5 different values of x. So in this case, then G is equal to 5. So what I can do is simply create a data frame that puts the high school GPAs in there. I find G. I could have just said G gets 5. Instead, I said G gets the number of rows of more.GPA. And then use the predict function as what we've done before. The key part there is the confidence level. Use 1 minus alpha divided by g instead. So what I have here are 5 different 99% confidence intervals, and combined together they have at least 95% confidence overall that their corresponding expected value of y is within inside the intervals. We could also do the same thing with prediction intervals. Again, the thing that changes is that the number of intervals that you want, you put that in the appropriate spot of the quantile for the t distribution. I'll let you read the example on your own. Okay. So back in chapter 2, we have the following plot. Let me blow this up a little bit. And we were looking at confidence interval bands. So for all possible values of x, let's find a confidence interval for the expected value of y, or prediction interval for y itself. How can we use the Bonferroni procedure here to control the overall family confidence level? What's G? Nope. We had 20 observations. G's not 20. Because I'm actually finding all possible intervals from the smallest x value up to the biggest x value. Sorry if that wasn't clear. That's what we did back in chapter 2. So what's G? Infinity. What's going to happen then if you somehow stick infinity in for G in our formulas that we were seeing? Well, you're going to have some quite wide intervals. It'll be hard to draw. So would the Bonferroni procedure work in this case? No. And this is, though, where that Chaffee procedure that I briefly mentioned would work. And again, if you're interested, take a look at the book. Okay. So the first main topic in Chapter 4 was how to control the overall family confidence level. The second topic, which we are not going to spend time on, but I just at least want to briefly mention, because I think we've even had a question regarding it in class, and that is regression through the origin, section 4.4. Sometimes it may be known that x is equal to 0. And this is especially important for cases where in your actual sample itself, x equals 0 does exist. And if you know that at x equals 0, y must be equal to 0 too, you can actually incorporate that into your regression model. And the way you do that is, as you would expect, you just take out that beta 0 that we had before, and now this forces then the regression model to go through the origin. X equals 0, y equals 0. Make this 100% again. So how can you tell R that you do not want to estimate beta 0? And I think I've mentioned this before. And that is with the LM function, when you say formula equal, suppose your response is y, suppose your predicted variable is x, you just put in it also a -1. And that's just a syntax to let you know, or let R know that, okay, don't estimate beta 0. Alternatively, you could also do this. Formula equal y tilde 0 plus x. So again, it's just syntax to somehow tell R that, hey, don't estimate this beta 0. Again, though, but most often, it is not known that the model should go, through the origin. So often it's just safer to say, okay, why don't you just go ahead and estimate beta 0? And if truly, when x is equal to 0, y should be equal to 0, well, what should beta 0 be? What should its corresponding estimate be? Approximately 0. So in the end, it's not going to hurt you if you leave beta 0 in your model. Okay, section 4.5. Another section we are not going to do, so you're not responsible for this. But I do at least want to mention, because maybe when you do research or maybe you come across in other classes, this might pop up. And that is, there are cases where when you're measuring your X or your Y in terms of you are taking your sample, you might not get the measurement right. A classic case that's often talked about is, let's say that you are timing the 40-yard dash times for football players, and you're doing it with a handheld stopwatch. Well, that's not going to be as precise if it was electronically timed. So you can think of this, that you are obtaining some kind of measurement error, because when you're timing with your stopwatch, it's not going to be correct. Exactly. Well, how do you account then for the fact that you might have a measurement that's actually incorrect? Well, if it's just with respect to your Y's, it's no big deal. Basically, that epsilon, remember that's a random error term, that basically, that error that you get in your Y just goes right into your epsilon. It's really no big deal. But where it can be a big deal, though, is when you're dealing with your X's and you have a measurement error there. That can cause some big problems. There's a whole literature on the subject of how do you account for measurement error in your predictor variables. And in fact, some bigger stat departments I've seen, or some very large stat departments, I've seen them actually have whole classes on it. So it's kind of hard for me to go into the details about what do you do. And basically what happens is that you assume something like this. That you let X now be a function of, let's say, the true value, let's call it Z for the lack of another letter, plus a random error term for that, which has maybe a normal distribution, or you could actually work with other distributions as well. And so that's how it's handled. But estimation then becomes a lot more difficult. And again, we don't have time to get into the details of how to work with this. If you want, here's a classic reference on it. Okay, now here's something that we are going to do. It's called inverse prediction. Kind of an interesting problem. So far we've been focusing on using our predictor variable to make predictions about our response variable y. But there are times where, let's say you do have a sample model, and you somehow obtain a new value of y without knowing what x is. Well, since we have this mathematical relationship that we come up with our sample model, you might think, well, maybe I could use this sample model to, let's say, inverse predict what x would be. And in fact, you can do that. Here's how. So let's say I have a new, let's say, y value, and this is the book's notation. They call it yh new. I'll just say y new. It's just easier to say. And you want to predict, well, what will be the corresponding x value, which our book denotes as x new. Well, again, we have this mathematical relationship that we're working with respect to our regression model. So you might think, well, how about we just solve for x? And we can do that, sure. X is equal to y hat minus b0 divided by b1. Well, how about we just simply replace this y hat with this new value of y that we've obtained, and if we do that, we get out a predicted value then for x. Notice how I put a little hat on top of that x to emphasize that this is now predicted. Predicted because obviously b0 and b1 were estimates based upon your sample. And as you might expect, that this prediction is not going to be perfect. It's not going to get at x new exactly. So what do? We form confidence intervals for cases like this, just like what we've done in the past for other similar situations. So one can show that the approximate 1 minus alpha times 100% confidence interval for x new is this expression here. Notice the form. As we've seen before, we have an estimate. We take plus or minus a value from some distribution, in this case a t-distribution, times the square root of the estimated variance of the estimate. That's a very common form that we use for confidence intervals. This is what the actual expression looks like for the estimated variance. It's not necessarily the prettiest thing in the world. Don't worry about derivation. So that's what it looks like. Note that you have an x hat in there as well. This x bar represents the mean of all your x's in your original sample. And notice in the bottom here we're taking basically the sum of squares for the x's in your original sample. Well, let's take a look at an example where this might be of interest. Inverse prediction is often used in trying to calibrate an instrument. So oftentimes, you might have some kind of instrument that takes a measurement, let's say, and this particular instrument is very, 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 very good, very precise, but it might cost a lot of money to get it to take a measurement, or it might just cost a lot of money in terms of the actual instrument itself. And so because of that, you might want to maybe develop some other less costly instruments to take the same kind of measurement, but it might not be as accurate. And so what you might want to do is figure out, well, kind of how good is this new instrument that you developed? So this is a classic example. I actually got this example out of another regression book. Let's suppose a thermometer is being calibrated to determine if it's reliable enough for a physician to use with patients. It's placed in a water bath at a known constant temperature, so somehow we have some other kind of instrument that allows you to get the exact temperature. And so we know what the exact temperature is of this bath. And we're going to use now this new thermometer to record the temperature as well. So when the bath was at 96 degrees, the temperature that we got was 95.71 from the thermometer. And we did it up to 110 degrees, and our thermometer had 110.21. Okay. Again, this example from another book. And let's just say that the thermometer is meant to be used later, and wants to let's say use it on a patient, and this patient through the thermometer had 104 degree temperature. What we want to know is, well, what's the actual true temperature of that person? So this is where inverse prediction could be used. What we want to do is find a 95% confidence interval for this x nu, the actual temperature. So let's talk about how we can do this in R. First, I could have the data set, let's say, in an Excel file, or I could have it in just a plain text file. In this case, this is just such a small data set, I decided to simply type it into R. Simply how you can do that, create an object called, let's call it set1, get a data frame, where I'm going to create one variable called y that has all the y values in there. And then also a variable x that has all the x values in there. And let's just run this to make sure that it worked. There we go. Then let's estimate the model the usual way. I'm going to save the summary of the results into sum.fit. And let's actually look at sum.fit. So we can see that my model is y hat is equal to negative 3.14 plus 1.03 times x. Okay, now let's do this inverse prediction. Unfortunately, there's not a function R that will automatically do it for us. So this is where we're left with just simply programming in the corresponding equations. So to begin with here, let's define what y is. 104. I'm going to use an alpha level 0.05, find my sample size, and then find x hat. So y minus B0 divided by B1, and this is what I get. $103.99. So pretty close, obviously. Note that you see the word intercept there. I think we've seen cases like this in the past. This is just a leftover label coming from mod.fit $ coefficients. You see the word intercept there. How can you remove that from being printed? Simply you can do something like this. There's other ways too. Use the function as.numeric, and that just tells R, treat this as just simply a numerical value, forget all the labels. That's all. Not a big deal, but it's just a little annoying to have that extra label there. Then what I need to do is actually program in the confidence interval formula into R. Get the formula out here. Just some of the highlights, I guess, of doing the programming. Notice again that we need this sum of the xi's minus x bar squared. Notice how I get that simply. I take the variance of my x's in set 1, take it times n minus 1. So remember that basically just gives me my numerator, my sample variance formula. Then I pull out sum.fit $ sigma. Remember what that is? That's the square root of MSE, just the sigma part there. So I square it to get MSE, so it gives me this. I divide by B1 squared, and then I multiply by everything that was in that brackets, just arranged correctly. Would anybody like me to go through the details? I'd be happy to. Okay. Of course, make sure that you can run this on your own, that you know how to use it, you understand what the formulas give you. And in the end, here's my confidence interval, 103.4 to 104.59. Now, one can actually see this on a plot. This is on page 17. This helps just emphasize what we're trying to do here. So the circles there are the actual observed data values. The red lines is the estimated, the sample regression model. And remember we had YH new was 104. And so we're doing inverse prediction. So we're starting from the Y's and we're going over to the line, and to find the corresponding X we project down, and there's 103.99. The little marks right around that 103.99 corresponds to then the confidence interval itself. How did I get this plot? It wasn't too difficult. First, I don't know if I've mentioned this before, just some R coding stuff. We've talked about the par function before, I believe, in this class. Does that sound familiar? Okay. I'm seeing some people shake their head up and down. Other people are just giving me blank stares. So I'm assuming that we have. PAR stands for graphics parameters. And there's three arguments that we have not talked about, I don't think. PTY. Anybody know what that stands for, maybe? Excuse me? Point what?
Y.
No, not exactly. Plot type. The S value says make it a square. So you notice the plot itself is a perfect square. And so why did I do that? Well, it's because we have both X and Y measured on the exact same scale. So it made sense to do that. The default value is M, which stands for maximize. In other words, it will maximize the plotting surface, or the plotting part in the window. So just to show you what happens. So this is the default. Now, if I actually run it with the PTY argument, you can see how it's a square. So just a small thing about graphing. The x-axis argument, I give it a value of I, and that just corresponds to, it tells R that you want to specify the axes to start and end at exactly where you say. So notice here for my x lim argument, I specify 95 to 112 and 95 to 112. Now by default, let me change it back to the default real quick. The default is what's an argument value of R, and you can see the effect. Basically what it is, I think it's R, if you specify 95 to 112, it actually goes out about 10%, 12% larger or less than from where you specify. Just to make sure that you get the points on the plot. I guess that's why that's done. So you might be thinking, why am I telling you all these little nitty-gritty details of how to use R? Well, most of you will be writing papers for journals, and in these papers that you write, you're going to probably often have plots, and you want to make sure the plots look nice. Well, how do you do that? You have to learn, the basics of the various arguments and various options. So that's why I take the time to talk about this. Okay, so let me remove that. So this is what I get for the basic plot. I want to add some stuff to it. In particular, it would be nice if I actually saw tick marks for 96, 97, 98, 99, and so on. And we talked about this in the Introduction to R lecture that we had. We can use the axis function to do this. Side equal 1 corresponds to the lower x-axis. I want to draw tick marks at 95 to 112 by 1. I do not need labels there. I want the lines to extend 0.25 inches down. So let me show you what happens when I run that. Now you see the little tick marks. And especially on a case like this, it helps you read the graph a little bit better. I can do the same thing for the y-axis. I can also plot the model using the curve functions we've done before. And then lastly, what I want to do is actually show this inverse prediction. So to do that, I can use the segments function, which we've seen before as well, and simply draw line segments. I want a line segment that starts at x equals 0 and 104 degrees. I want to draw that line segment to 103.99, the predicted value, and the y-axis value will be still 104. I'm going to make it a dark green line, and there you see the line drawn. So the second segments function draws the line down, and then lastly, to get points, or to get the confidence intervals drawn on the plot, I use the points function. This allows me to just simply draw new points on the plot. Where do I want the points drawn at? I want them drawn at the actual confidence interval value. So save.ci corresponds to where I put the actual confidence interval. So it has a lower value and upper value. I want to draw it on the y-axis at 95.1. And what points do I want to use for a plotting character? How about we use parentheses, because that kind of looks like, interval, the sides of the interval. And this is what I get. And so there you see that added to the plot. Okay. Are there any questions? Yes?
Is it possible to change the label fonts over there?
The labels
The font.
of the font? Yes, it is. I have actually done that for journal articles, for plots that I've drawn. I don't remember how to do it off the top of my head. I'll post something in the listserv. generally speaking, I have not had any problems with using the default fonts for journal articles for plots. And if you pick up any statistics journal, typically the plots are done in R, and they use the default font, so you can see that yes, it's R. But for one paper, just because I was curious about how to do it, I did figure out how to change the fonts, and I need to go look back at my corresponding program that did that. Other questions? Okay. That's the end of Chapter 4. So it was real quick. Let's go to Chapter 5. Okay. Starting in Chapter 6, we will do multiple linear regression. We'll do that for the rest of the semester. Again, multiple linear regression means you have multiple predictor variables. In order to go to a multiple predictor variable setting, it's going to make it a lot easier if we basically do all the stuff that we've done so far in the context of matrix algebra. Now, you might remember on my syllabus I put, for prerequisite, matrix algebra is something that will be very, very useful. And this is why. Because now for the rest of the semester, then, we're going to be using matrix algebra. There's probably a variety of backgrounds on matrix algebra by students in this class. Some of you probably, a lot of you have probably had a full-fledged undergraduate matrix algebra class. Others of you, maybe you've just seen a little matrix algebra here and there that you need to learn on your own to do stuff. So, what I have here, and this corresponds to what the book does, I have a little review of what matrix algebra is. So for some of you, this is going to be quite simple. Others of you, this might not be. But for probably all of you, how to do matrix algebra in R will be new. So, if you're used to matrix algebra, focus on the R part. For more information, too, beyond what I'm going to talk about in our class, you can see Fox and Weisberg's section 8.2 in their book on matrix algebra and R. Again, this corresponds to the recommended book for our class. That wasn't required. Okay, so what is a matrix? Back when I first started teaching regression analysis, it was about time that the movie The Matrix came out, so I always got to say, what is the matrix? As the beginning here, but now it's after the sequels, it's not as much fun to talk about the matrix. Those sequels were not very good. But anyway, a matrix is a rectangular array of elements arranged in rows and columns. Simply put, here is a matrix. I just have the numbers 1, 2, 3, 4, 5, 6 arranged in 2 rows, 3 columns. Often we refer to this as a dimension 2 by 3 matrix. We always put the number of rows first, the number of columns second. Okay? We can represent a matrix in symbolic form. We always will use a bold letter to denote a matrix, a bold uppercase letter to denote a matrix. So in this case, we have a matrix A. It has elements that are written in there as well. Notice we're using lowercase letters for the elements of the matrix. And notice the subscripts there too. They correspond to the row number and the column number. We always put row number first, column number second. So A sub 2, 3 is the row 2, column 3 element of a matrix. Now, oftentimes we might just want to, if you're just writing out stuff yourself, maybe on a piece of paper, or you're doing a test in this class, and you want to say, I have a matrix A. Well, how do I know that's a matrix A when it's not bolded? This is kind of hard to bold. I mean, you're not going to, on the test, do that, okay? Instead, the convention of what people usually do is when you want to represent, just from writing, a matrix, you put a little line under it to indicate, okay, this is a bold. This is a bold letter. Here's a very general form of a matrix. This is an R by C. Typically, when we want to say the number of rows and number of columns, and we want to be very general, we use R for number of rows, C for the number of columns. We can have square matrices, meaning simply the number of rows is equal to the number of columns. So let's look at this in terms of the high school and college GPA data set. What we're going to be working with is a particular X matrix when we do regression analysis. And in the context of this particular data set, our X matrix is going to look like this, where this corresponded to all the the second column corresponds to all the predictor variable values. The first column is a column of ones. You might be thinking, why do we put a column of ones there? Well, just stay tuned. It will make sense. We probably won't get into it today, but it will make sense on Thursday why that's a column of ones. And so our X matrix, which contains our predictor variable values in this column of ones, for this particular case is a 20 by 2 matrix, 20 rows, 2 columns. A special case of a matrix is what's called a vector. You've heard me use that terminology already with respect to R. We have to be a little bit careful about what R calls a vector and what a vector means mathematically. More on that coming up. Simply, a vector is a special case of a matrix where maybe you only have one column or maybe just one row. So a column vector is an R by 1 matrix. So in other words, you just have a column, let's say, of numbers. A row vector means that you basically have just a row of numbers together in a matrix. Sometimes you'll see when we have a vector, the second subscript for those elements will be dropped. Just please note that. When we do this in regression analysis, in particular the high school and college GPA, we will have a vector called Y. Y is going to contain all of our response variable values. It's often going to be useful to us to calculate to do what's called a transpose of a matrix, and that just means simply the rows become the columns and the columns become the rows. So for example, if I have this matrix A, if I take this row and now put it as a column of a new matrix, I'm basically transposing that row. If I take this particular row, make that the second column, now what I have is the transpose of the A matrix. How do we denote transpose? Our book uses a little tick mark there, or a prime, so I'll call this A prime. Other books, sometimes you'll see them actually put a little T there instead for transpose. Our book uses the prime mark. So note that A is a 2 by 3 matrix, A prime is a 3 by 2 matrix. So for example, there's Y prime in the context of the high school and college GPA data. Now we will want to do a lot of numerical calculations with these matrices. That's what's going to make things easy for us when we have multiple predictor variables. And so, stuff like addition, subtraction of matrices, we're going to multiply matrices together, and these are just the extensions of what you learn about multiplication and addition and subtraction in your grade school days. So for example, if I want to add or subtract a matrix, let's say I have two matrices, A and B. To add these matrices together, first of all, they need to be exactly the same dimension. That's a key part. They need to be exactly the same dimension. Notice they're both 2 by 3s. And then all you do is simply do element by element addition. So 1 plus -1 is 0. 6 plus 8 is 14. And you can do a similar thing with subtracting matrices. Let's talk about how we can do this in R now. Okay. So to create a matrix in R, you have to use a function called matrix. Makes sense? And we want to put information in this matrix. Often it will be data. So the main argument in the matrix function is called data. And this is where you can put in your elements of your matrix. So in the case of this A matrix that we saw the numbers 1, 2, 3, 4, 5, 6. Notice I am combining them with the C function. I purposely, now I could have done it like this as well, but I purposely hit enter here and lined them up just to help me see the elements of the matrix better. That's all. I specify the number of rows that I have, 2, the number of columns, 3, and the last part's critical. By row equal true. That tells R how you are arranging the elements inside the matrix. So for example, notice that 1, 2, 3 goes in the first row. 4, 5, 6 goes into the second row. If I were to take off that argument, the default is by row equals false. And look what happens. Now things go by column. So that 1, 2 becomes now the first column. So you have to be careful about how things are arranged. It's just syntax. You just have to get used to it. Remember the class function that we have briefly looked at before in Chapter 1? Class of A is matrix. So that just shows you that indeed that this is indeed what R calls a matrix. I can also do B, and if I want to take A plus B, well, I use A, the plus sign, and B. And there's exactly the same result that we had on page 5.5. Okay. Now you can also create vectors, mathematical vectors, using the matrix function R, as you would expect. So for example, let's say that I want to create a vector Y, and it's just simply going to be the first row of A. So I just take 1, 2, 3, number of rows, I'm sorry, it's going to be a 3 by 1 vector, excuse me. So I'm going to have a column vector, 3 rows, 1 column. I'm going to put that into Y and look at the class matrix. I'm sure that's all y'all expected that. But the reason why I bring this up is this. Suppose I do this instead. X gets 1, 2, 3. Remember, I've been previously calling this as a vector. Let's see what happens. Notice the differences here. You can see the columns, you can see the rows as R gives them. But now, by just simply using the C function, you just see basically a set of numbers. Well, this is because, notice the class here. It doesn't say matrix, it says numeric. This is because R has something called a vector, and a vector is different from a matrix in terms of the class structure. That obviously can be a little bit confusing. In the end, for us, it's not going to be that big of a deal, but I do want to bring this up because it might pop up a few times in this class where, okay, this is why R is not doing what we expect. There is a function R called is.vector, and it just gives you a logical check. Is it a vector or not? And so, yes, it is. If I did is.vector Y, no, we had false, because it's actually, in R's terminology, a matrix. And where this comes in, or where this can make a big difference for us, is in the next section where we do what's called matrix multiplication. So stay tuned for that, but I want to point it out now first that this little aspect happens. If I want to take a transpose of a matrix, I just use the t function to do the transpose. So, well, what does our regression model then look like if we were to write in terms of matrices? So this is the first time that we've done this. So previously we've written out our model like this. Y sub I is equal to expected value of y plus epsilon sub I. Of course, expected value of y sub I is beta 0 plus beta 1 times x sub I. Well, we can write this, and this is for sample size of n. We can write this now in terms of a matrices. The bold y is equal to expected value of bold y plus bold epsilon for emphasis. This is our model, right, in terms of matrices. We'll look at other examples later. Okay, section 5.3, matrix multiplication. First of all, we need to find what's called a scalar value. Scalar is a special kind of a matrix too, but it's a very small matrix, simply a 1 by 1 matrix. So just simple numbers like 3, 5, 7, those are referred to scalar values when we're talking about matrix algebra. And if I want to take some kind of scalar, let's call it C, and multiply it by a matrix A, simply what you kind of expect happens, where every single element gets multiplied by C. So for example, if I had a matrix A, if I take 2 times A, notice how every single element of A was multiplied by 2. Now here's something that, if people are totally new to matrix algebra, might seem strange at first. And that is, how can we now multiply 2 matrices together? Okay. Well, let's say I had 2 matrices A and B. I could denote their multiplication symbolically as simply AB, or I could put, some kind of multiplication symbol between them. Now, let's say that I call then the result from A times B to be equal to some new matrix C. Here's how you can do matrix multiplication, explained through an example. So here's my A, and here's a B. Now to do matrix multiplication, it's very critical that you have the correct dimensions to your matrices. So A is 2 by 3, B is 3 by 2. In order to multiply 2 matrices together in terms of A times B in that order, you need these numbers to match up. So the number of columns in A has to be equal to the number of rows in B. Here's why. What we're going to do to find our new matrix that we get from multiplication is that we're going to take the first row of A and simply multiply it by the first column in B. Element by element multiplication. And then we're going to simply sum the elements together. So I'm going to take 1 times 3 plus 2 times 1 plus 3 times 0. Add them up, I get 5. And that becomes the first entry of my new matrix, C, the result from A times B. Next, I'm going to take the second row. I'm sorry, I don't want to do that. Excuse me. I want to take now the second, the first row, and multiply it by the second column. And that gives me, and then add up the corresponding results, and that gives me a value of 7. And I'm going to keep on going here, and since I have all these nice little colors that I have to choose from, I can take the second row times the first column and get this. And then lastly, let's do yellow. Probably won't show up very well. The second row, second column becomes the to 2 elements of my new matrix. This is how you multiply matrices together. Now, will I ever ask you to multiply a matrix together by hand on a test? What do you think? Do you want me to? Okay, we will. No. I might say, show me how it's done for a very small matrix. That's the extent. But we're typically going to use R to do the multiplication for us. But you at least have to have a basic sense of how this multiplication is done. And so that's why we go through this example. Now notice here, the result was a 2 by 2 matrix. Well, where did that come from? Well, it comes from the number of rows of A and the number of columns of B. So you always know then what the result will be in terms of the size of the matrix. So again, to review, the critical parts are you need to have the column of A to be equal to the columns of A to be equal to the number of rows of B. And then do what are called cross products of the rows and the columns. In other words, multiply the rows together and then add the corresponding totals. And then the resulting matrix then is the number of rows of A and the number of columns of B. Okay. Note that, when you first learned about multiplication, you saw that 2 times 3 is equal to 3 times 2 always, 6. But when you're working with matrices, that no longer happens, generally speaking. So A times B does not equal B times A. So please be aware of that. And just to show you that, indeed, that's true, there's B times A, and you can see how it's a different dimension, 3 by 3. Okay. So there's a very general representation then of how the matrix algebra was done. When we hold off on doing the R example, are there any questions? Okay, that's it for today.